Hi. So for the first part of the course, I want to discuss what are a principled way to help identify the critical regions for spike propagation in the axonal segments. So what I'm going to present is a summarized version of what you can find in our published paper from me and Nathan from a couple of years ago in the Journal of Computational Neuroscience. I'll leave the link down here on the description for you. Okay? So what is the big picture? The big picture is that we discussed those anomalous changes in axonal morphology, the focal axonal swellings, and we expect that the swellings are going to change the content of the spike trains. Okay, so here are spike trains coming in the top of the axon, and this is and they're traveling downstream. And if this were a healthy system, we would expect that the output spike trains would look pretty much very similar to the input spike trains, and that nothing very complicated happened through that trip. Okay, but due to the complicated geometry, a lot of anomalous effects can take place. So for example, we might expect some spikes to be deleted, some spikes to be shifted, some spikes even to be created, and therefore we expect that the output spike trains to be really different from the input spike train. And this is very serious because we're talking here at a fundamental neuronal level that we're going to have already problems in transmitting and encoding and then constantly decoding everything that the neurons are trying to convey to their neighbor neurons, and this eventually is going to cascade from a cellular level to a network level to a systems level and cause maybe the total dysfunctionality of the system. Okay, so what we're going to do is we're going to use tools from computational neuroscience and applied math to try to study this thing in a little bit more of a systematic way, okay, and try to identify what are the regions that are worse for spike propagation. Okay, so if you ever took a course in computational neuroscience, you probably studied the book of Day and Abbott is one of my favorites, and you probably studied a little bit of cable theory. And the idea is that, well, if this is our neuron, and if we zoom in one of these cables, right, we can write a partial differential equation that models the spatio-temporal dynamics of the voltage of V along the membrane of the neuron. Okay, so the variables here are the voltage V. That's what we're going to solve for. Okay. And we have the space variable x, so where we are in space. We have time, and since locally the axon looks like a cylinder, we can assume that, yeah, locally this thing looks like a cylinder of radius a. We're going to study like a cylinder of varying radius with varying a later on. Okay. And some other circuit properties of the system include the resistivity RL, the capacitance CM, the external current, and the membrane current IM. Okay, so the way you derive the cable equation, you basically it's an argument of like conservation of current. Okay, so you're gonna look at the longitudinal current is the current flowing on the left minus the current flowing on the right, and the sum of currents is the currents needed to charge the membrane. So if there's any changes here in this flux, it's because there were currents coming in and out from the membrane that disrupted the system. Okay, so this is the basic conservation scheme, conservation of current equation, and then you take the limit when delta x goes to 0, okay, and you can look at Day and Abbott for the details, and you will obtain some version of like an inhomogeneous heat equation, but for the voltage. Okay, so here you have dV dt, and this is kind of like the heat equation. So here you have the first derivative in x, here you have a second derivative in x, so this is roughly d2v dxx, except that this is inhomogeneous because we have a possibly varying radius. Okay, so A of x is varying here, so we have this inhomogeneous spatial operator right here. Okay, and then the other terms are the ionic currents and the external currents, and this is a very sophisticated system, and I'll try to and I don't want to study this too much in details here because you basically would need an entire course in computational neuroscience for that. But let me just point out here some important properties. This is a system, so we're looking at a system of a partial differential equations, okay? And here we have the spatial operator is modified to include the geometrical inhomogeneities. And we have ionic currents that are nonlinear, and they make the problem way harder and practically impossible to solve it analytically. Okay, and on top of that, so these nonlinearities come because well, there are some things called the ionic channels, and to make a very long story short, there are different concentrations of ions inside and outside the cells, and as you change the voltage, these ion channels might open and close in different ways. And the minute you start opening these ion channels, you're gonna have influx and outflux of these ions, and they're gonna and this is gonna create a very rich dynamics, okay, which is gonna produce the action potential, the spike, okay, which everyone studies on like the basic neurobiology textbooks. Okay, so from an equation point of view, these ionic channels are the dynamics of the ionic channels are governed by these auxiliary variables WJs. So you have different ion channels for all the different types that behave differently, that have different parameters, and these ion channels might open and close. Okay. And this equation is coupled, so you have the V and the W's, they're right here. So you have a coupled system of nonlinear partial differential equations. And the only way we can solve this is probably numerically. Okay, so to give a little flavor of what these dynamics here for the gating variables look like, the idea is that, well, these ion channels, they, in a very simplified model, they can be either closed or open, and depending on the voltage, you might have you might change the dynamics of how many channels are open and how many channels are closed. Okay, so typically those variables are the fraction of open subunits. So as you change V, you change the parameters alpha and beta, and you change the fraction of open subunits, so then you might have more or less influx or more outflux of these currents, and these are going to generate non-trivial nonlinear interactions between the voltage that will rely on like kind of like hyperpolarization and like allow it to generate the spikes, and then that spike to travel along the axon. Okay, so so to solve this, we are going to use a pseudospectral algorithm. So let me just outline this very briefly if you're not familiar with a pseudospectral solver for PDEs, although this is fairly common in optics, for instance. Okay, and so here's our system of partial differential equations, and what we're going to do is we're going to denote the vector of variables, so V and all the other auxiliary variables, as a big vector U. And this, and here for the Laplacian, we're going to, the inhomogeneous Laplacian, we're going to denote this by a linear operator L, okay? And this piece here that contains the nonlinear functions, we're going to call that the N applied to U. Okay, so we have now, so if we do this, we can recast these equations into the form du dt equals Lu plus N of U, okay? And it's a more concise form, and the pseudospectral produces the following time-space discretization. You're going to determine the desired discretization, so how many points, how many the resolution that you want, and both in time and in space. Okay, You're going to determine all the biophysical parameters that you need, so the resistivity, the conductivity, the varying radius, etc., etc. You're going to apply an external current to a small spatial region, let's say kind of like on this far end here of the system, and that should form a little pulse, and that pulse is going to travel around. Okay, so how do we evolve this in time? Well, you're going to Fourier transform this equation, and you're going to obtain a Fourier mode system of ODEs, because and the idea here is that when you take the Fourier transform of the spatial derivative, it just multiplies by I, right? And so then the PDE becomes a ODE into the Fourier domain. Okay, so the spatial variable becomes just an algebraic expression in the Fourier domain, and then you evolve this thing with your favorite ODE scheme, and so we used MATLAB's ODE 45. Okay, and it's important to note that because the system is nonlinear, that this nonlinear term here is going to couple all the Fourier modes. Okay, so the idea is that you're going to evolve this equation on time. So every time, and because you have this nonlinear term, you're going to have to, well, basically the idea is to evolve this on the Fourier domain, and once you solved for U hat, and then you have U hat, you would inverse Fourier transform your variable to obtain the solution for the system. Okay. Now notice that you have to apply the inverse Fourier transform U hat at every time step delta t, because you have to evaluate the nonlinearity. So that makes the method significantly more expensive than if we were just solving like a linear system. Okay. So the novelty here then is that we are going to add a varying axonal cross section. So we're going to look, so basically we're going to parameterize a swelling using these parameters: diameter before, diameter of transition, and diameter after. And we're going to try to approximate the shapes that we observe in the experiments by forms like this. Okay, so if you want to know the expression, here we have a of x given by this, and so we have the diameter before, diameter of transition, and the diameter after, and this function right here kind of like smoothly connects the diameter before to the diameter after, giving a width of approximately delta t. Okay, so what we did on our paper was basically a systematic studies of what happens if you start changing these parameters, so that we can start comparing which swellings are more dangerous than others. Okay, so I'll take a minute here to show you some axons from the work of Shepard and Harris, and notice how rich the geometry of these systems are, right? So the geometries vary wildly. Okay, so look that here you have like a really big varicosity right here. You have kind of like a weird shape of kind of like of a nose here of this axon. Here's another big shape, and look at this thing. This is really interesting. This is also really interesting. And notice that this guy right here, even if it's not very small, it's kind of like it's really pointy. And the question is, well, look at all these changes in geometry, and some of them seem to be bigger, but others seems to be a little bit more abrupt. And the question is there a systematic way that we can kind of like create a hierarchy, and so that when we look at a very rich set of axons like this, we can easily spot which are the most dangerous and most accessible, where the danger zones in which we expect the spike train propagation to fail. Okay, so what we did then is we did a systematic evaluation. So we explored the parameter space for all these three parameters here: the diameter before, diameter of transition, and diameter after, and we investigated what happened with the spike with the spike. Okay, so here in most of the scenarios, so if you don't have any abrupt change in geometry and the cable is somewhat more or what constant, you'll get a spike traveling more or less normally. Okay, so here is where, right here, when you see this little bending here is where they meet the change in geometry. So this little change over here. But this change in geometry, kind of like denoted here on the cartoon, wasn't enough to cause any trouble to that spike. It adjusted its profile and it started propagating a little faster, and that's basically what happened. Now, this one is an interesting case because you see a somewhat big change in geometry. So it goes from a relatively small diameter to a relatively large diameter. However, there was a long transition diameter, and that allowed the spike to kind of like change its profile and still make it to the other side. So even if the change in geometry was big, it wasn't too bad because it didn't happen very abruptly. It happened slowly, and and the pulse was able to adapt and continue to continue to propagate. Okay. Now, depending on how you pick the parameters, some other interesting phenomena can happen, and in this case, you can have reflection of spikes. So when this spike started traveling right here, reaches the change in geometry, the spikes basically broke into two. Okay, so one of the spikes continued to propagate forward, while the other spike went backwards. And that was pretty incredible. Okay, so here is another geometry of slightly different parameters in which we observe the same effect. So here you have the spike traveling. It splits into two. One of them propagates forwards, the other one propagates backwards. Okay, and finally, if you have a change in geometry that is too abrupt or just too big, you can have the spike being blocked at the swelling. Okay, and that would totally disrupt the propagation of information. So what we did was we explored then the parameter space. So we changed all so we looked at what were reasonable values for the diameter after, the diameter before, and the diameter of transition. Here are normalized units. Okay, and what we noticed is that, well, this is kind of like how these three different regimes occurred. We had basically a very thin region that looks kind of like a bended sheet of paper in which the reflection occurred, and if you were above that region, that means that the changes in geometry was too much or too abrupt, you would observe blockage, and if you were below this reflection sheet, then your change in geometry was not that critical and you would still transmit. Okay, so because this looked as a bended sheet of paper, we fit the best plane to the data, and we obtain a very nice, concise, simple function that we can use to evaluate how dangerous a swelling is depending on its parameters delta B, delta T, and delta A. Okay, so this is kind of like how it works. You evaluate that function for the parameters, and that's going to give you a regime number, which we're calling eta. Okay, and if eta is negative, then you're going to observe blockage. If eta is near zero, you might experience some reflection, and if eta is bigger than zero, then you're going to have transmission. Okay, so this now allow us to go back to the figure with the rich geometries, and we can now compare, okay, the different regimes. Okay, so here I selected a few of these swellings, okay, and here's the diameter before, diameter of transition, diameter after, and extracted these parameters, and then guess what? These guys here allowed for transmission, these guys here allowed for reflection, and this guy here gave us blockage. Okay, so I guess like the nose was the worst thing that we found, and even if it's not a huge change in geometry, it happened very abruptly. It came from a very thin axon, and the jump was really big, and that was more dangerous than something like this that even though it had more change here on the diameter, the change kind of like happened in way slower. So the physicists like to call it in a more adiabatically way, and that wasn't and the pulse was still able to polarize the membrane. It was and it still was capable to continue to propagate. Okay. So this gives us a nice little clean criteria to classify all these different swellings, which we wouldn't have much intuition without it. And this also gives a somewhat principled method to detect the critical regions in each axon. So here, for instance, we go over the axon and we extract the diameter before, the diameter of transition, right, and the diameter afterwards along the axon, and we try to calculate eta based on these images. And we know that if eta is bigger than 0, that we expect transmission. So on this part here, for this part here, we don't expect much trouble because we have large values here of eta. But then here we start, here you might get some reflection right here, okay? Then here you're starting to, you're critically close to the reflection sheet, okay? And here you're safe, transmission should happen safely, right? And so all you kind of have to do now to kind of keep track of the danger zones is to look at how the eta number changes along the axon and figure out when it crosses the 0, okay? So right here, for instance, close to the nose, okay, the eta picked a negative number right here. So that's where we expect the spike to get blocked, and that's the most critical region in this entire axon, okay? And I guess almost of the entire axon data set. So here's a couple of other examples, and we should worry a little bit on this transition, right, in which reflection might happen, or maybe transmission or other effects might take place even if a single spike can transmit. Okay, and in here we kind of have okay, we expect some troubles right here, maybe reflection over there. Okay, and this gives us the important thing is that we created a somewhat easy way to evaluate a large number of swellings, right? Because we want to apply this to several neurons, to a bunch of neurons in a network, and figure out what's going on. Okay. Some interesting remarks. If you put an axon enlargement close to the reflection region, okay, so if you pick these parameters such that you live on the reflection sheet, and if you add a little bit of what I'm calling here wrinkles, so some small variations here on the radius, okay, some small fluctuations, then you get like a very interesting effect, and these wrinkles might kind of they are sufficiently enough, they can perturb the system sufficiently enough to kick you to other sides. Okay, so you start here at reflection, depending on kind of the size of those epsilons that you're picking, you might kick it from you might round it, right, for transmission if you make it a little smaller, and you can kick it to blockage, right? So so small wrinkles in the membrane could be used to actually regulate the entire signal processing of these units if the axon happened to operate right in this intermediate region between the two in this critical region between the two regimes. Okay, and another interesting thing that can happen is with reflection. You can have, well, I guess this is more of a mathematical construction, but in theory, if you have something that, if you have a green, if in this green region you get a spike that kind of reflects backwards, and here you have a decrease, so an enlargement on this direction that creates a reflection on that direction, on the opposite direction, you could potentially start having reflection from here, 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 and that's kind of like what you're seeing right here, right? You split into two, one continues going, one goes backwards. This guy, when it reaches here, it splits into two, one continues to go, the other one goes backwards, and so on. So you can actually get a spike trapped right here between these two enlargements, going back and forth, working as some form of a pacemaker, and or you can do that by kind of like maybe doing like small modulations on the radios like we see on the previous slide. So you with these features, you can actually build very complicated and very sophisticated units. Okay, but well. I'll leave it to this right now. Thank you very much for watching this.